Welcome all to MQ session 1AP. Please don't forget to leave feedback at the end of the session. And if you want to post questions, please use the chat room and Gideon will respond to them at the end of this session or during, if he so wishes. And without further ado, I'll hand you over to Gideon.
Okay, thank you very much. So my name is Gwydion Tudur. I work in the MQ development team, normally based in IBM Hursley, but at the moment, obviously, we're working from home still. So that session is going to be essentially an introduction to MQ clustering. Before that, of course, please consider donating to the GSE charities. But before that, let's get on with this session. And what we're going to look at is, first of all, an introduction to what clustering is and why you might want to use it, what the benefits are. And then we'll have a look at how it works and how you set it up in MQ, and then go on to look a little bit at some of the smarter things you can do around workload balancing and helping availability using MQ clustering. So let's start off by taking a look at one of the main benefits that you get from clustering in MQ, which is to make your life easier as an MQ administrator as your MQ estate gets larger and larger and more complicated. So when you start off using MQ, then things start off probably fairly similar to this. You have a queue manager, you've got some sort of service, an application which is servicing requests that appear on a queue, and then you'll have another application which is putting messages, and then also maybe expecting a response to come back on a response queue, a reply queue. So all very simple, but then over time you'll probably want to extend things so that then you have distributed queuing. You now have channels which move messages between your queue managers. And if you're an MQ administrator, what you need to do at this point is you need to define a pair of sender and receiver channels so the messages can go in both directions between the queue managers. You'd also need a transmission queue for each of those channels, and possibly also remote queue definitions as well, so that applications can put messages to remote queue managers. So there's a few more object definitions that you need at this point, but it's still fairly easy. You've only got a few of them because you've only got a small number of applications, a small number of queue managers. Of course, over time, things get a little bit more complicated. You might well add more queue managers because you want to, you have more load, so you want to add more queue managers for that reason, or you might want to add more queue managers for availability reasons, or also because you have applications now running in several places and you want to have your queue managers located closely to where your applications are running. So there's many reasons why your MQ estate grows over time. And of course, as that happens, then your job as an administrator becomes a little bit more complicated because you've now got more connections that you need to define and manage between the additional queue managers that you now have. So if you see in the diagram, even if you've got 4 queue managers and you want to have a channel in both directions between each of those queue managers, you've already got a number of channel definitions and also transmission queues that go along with those channels, and also probably some remote queue definitions to manage as well. And of course, things will over time inevitably get a little bit more complicated again because you will add more applications that need to use MQ as your business changes and hopefully grows. And that may very well mean adding more queue managers again for capacity or availability reasons, or one of several reasons why you might need to grow the number of queue managers that you have over time. And of course, what that means is, as I was saying earlier, that your job gets more complicated again to manage the connections between all those queue managers. So that's the channel definitions and the transmission queues, for example. So this is the point where you might want to consider using an MQ cluster just to make your life a bit easier as an MQ administrator, because when you have all your queue managers in a cluster, MQ essentially manages all that work of defining and managing the channels between the queue managers. So for any of the queue managers that are in the cluster together, they're able to communicate to each other without you needing to explicitly define a channel between those two queue managers, because MQ will implicitly define channels between any pair of queue managers within the cluster as and when they are needed for messages to move between those queue managers. Also, you can define queues within the cluster, and that queue is available to be used by applications connected to any other queue manager in the cluster. So you don't need to define any remote queue definitions, for example, to allow that to happen. So make things a lot easier for MQ administrators. We'll have a look now at how it works and how you set up a cluster. So first of all, at a high level, what do you have as components of a cluster? Well, first of all, you need to have two what are called full repositories. And full repositories are essentially just queue managers that are part of the cluster, but they're a little bit special in that they have a knowledge of all the queue managers that are members of that cluster. So they know all the queue managers that are members of the cluster, and they also know about queues that are shared as part of the cluster as well. And we'll look at that in more detail in the next slide. But first of all, you define your full repositories. You need more than one for availability, and put them somewhere which is fairly reliable as well, but you only need two. So the answer to how many full repositories you need is almost always two. So once you've got your full repositories, you can add other queue managers into the cluster. And as you add those queue managers to the cluster, then they will publish information to the full repositories, which essentially just says, I'm here, I'm part of the cluster as well. And the full repositories then have knowledge of all the queue managers that are part of the cluster. Now you probably need to define some queues now for applications to use to put and get messages. And you can define those queues as clustered queues. And what that means is that the queue manager where those queues are defined will publish information to the full repositories to say that I have this queue as part of the cluster. And once that information is in the full repository, then that queue is available to be used from any of the other queue managers within the cluster. So when an application connects to another queue manager that's in the cluster, it wants to put a message to that queue that's been defined. The queue manager that the application is connected to will ask the full repositories for information about where that queue exists within the cluster. It'll get an answer from the full repository, and it will then automatically define a channel to send a message over to the queue manager where that queue is actually defined. So if we look in a bit more detail about how you actually define the queue managers and all the other components that are part of the cluster. First step, as I mentioned, is to create your two full repositories. And the commands that you would use to do that is, first of all, you issue the auto queue manager command to tell that queue manager that it is a repository for this cluster called cluster1. And then you need to define a channel, a cluster receiver channel for that queue manager. Now you'll need to define a cluster receiver channel for each queue manager that's in the cluster. It's quite important, the information that you put on this channel definition, because it gets used by other queue managers to send, to create the channels to that queue manager. So the con name is important, for example, because that tells other queue managers in the cluster how to connect to this queue manager. And of course, you also need the cluster attribute, because that tells MQ that this channel is part of that cluster called cluster1. So at this point, you've got a full repository for that cluster. You can, or you should also define another full repository, and you do that using very similar commands. At this point, neither of them know about each other. They only have cluster receiver channels. So you now need to define some cluster sender channels so they're able to communicate to each other. And once you do that and the channels start up, then the full repositories become aware of each other. And now you have a cluster that contains two full repository queue managers. Now the next step is probably for you to add more queue managers into the cluster. So we have another queue manager called queue manager 1. What we need to do is to define the cluster receiver channel in exactly the same way as we did for the full repository. Now again, important that the con name specifies the location of that queue manager, because that con name will be used to create those automatically defined channels that send messages to queue manager 1. And then what you need to do is to define a cluster sender channel. Now, only one cluster sender channel is needed, and that needs to point to one of the two full repositories. Now, once those channels have been defined, then the cluster MQ can automatically define the other channels that are needed in order to get the connections between that queue manager and the two full repositories. So now everyone is aware of each other, and that queue manager is a member of that cluster. And there's a question in the chat about if two full repositories have performance issues, will adding an additional will improve things? Generally not, because the issue with having more than two full repositories is that the partial repositories, or the other queue managers in the cluster, only publish information out to two full repositories about things like queues, cluster queues that have been defined in them, and you wouldn't want information to be incomplete on some of the full repositories in your cluster. So the answer is almost always you need two full repositories. Adding more than that can possibly cause issues. Right, so the next thing you might want to do is to define some queues, obviously, so that applications can use some cluster queues to do some messaging work. So this is how you define a queue in the cluster. Essentially, you just need to include that cluster keyword on the command when you define the queue. And once you do that, then information about that queue will get published to the full repositories, and it'll be available to be used by applications connected to any other queue managers as they come along into the cluster. Now, there are some commands that you can use to view the status of things in the cluster. So we have the display cluster queue manager command, which gives you the status of channels, all those automatically defined channels, as well as the ones that you've explicitly defined for the cluster. And there was also a display queue cluster command, which, as you might be able to guess, gives you information about the queues that have been defined in the cluster. So those might be useful if you just want to know what's going on inside the cluster. Right, so you probably will want to add some extra queue managers into your cluster, and the way of doing that is very similar to what we did with queue manager 1. So you need a cluster receiver channel and a cluster sender channel to one of the full repositories. And there we go, that queue manager can now be part of the cluster. Importantly, queue manager 1 and queue manager 2 don't need to actually communicate at the moment, because there's no messaging work going on. Each queue manager only needs to talk to the full repository. So note that we have some automatically defined channels between the full repositories and the other queue managers, but not between queue manager 1 and queue manager 2 yet. Now, what might cause that to happen, though, is if an application comes along and it wants to put a message to queue 1. So we'll try to open that queue, and queue manager 2 will ask the full repositories if that queue exists in the cluster, and if so, where is it? So it'll get the answer from the full repositories, and at that point, MQ will automatically generate a sender channel from queue manager 2 to queue manager 1 that can then be used when the application puts a message onto that queue. And the transmission queue that's being used is the cluster transmission queue. So you don't need to define either the channel or the transmission queue for the message to go from queue manager 2 to queue manager 1. So all you needed, just to recap on that, is two full repository queue managers for your cluster, a cluster receiver channel definition on each queue manager in the cluster, a cluster sender channel definition for each queue manager in the cluster, and that's it, essentially. You don't need to create pairs of channels between each of the queue managers in the cluster for them to be able to talk to each other. You don't need to start your channels manually, because MQ does that as well, and you didn't need to create any remote queue definitions or transmission queues for the messaging to happen between two different queue managers in the cluster. So it does make your life easier in terms of administration and the number of objects that you have to define. All right, so we've looked at how it should make your life easier in terms of administering MQ. what else do you get with a cluster? Because there are some other benefits as well. We take this example where we have a queue manager with the queue on it and a service that gets messages off that queue. And imagine those queue managers are in a cluster. Now we might want to add extra queue managers in order to maybe improve availability or to allow more throughput to be processed by this service. So we can add another queue manager and another service that processes messages off that queue. Now, as this queue manager is in a cluster, and we have two instances of that queue, both named the same and both part of the cluster, that essentially means that we have two instances of the queue in the cluster, and a message that is put to that queue within the cluster can go to either of those two instances. So when client one puts a message via the queue manager on the left, it can end up going to either of the two queue managers on the right and be processed by either of those two services. And actually MQ does some workload balancing to ensure that as far as how many messages go to the top queue manager and how many messages go to the bottom queue manager, the number is quite even. MQ has a workload balancing algorithm that's used by the cluster in order to ensure that. Now, if one of the services becomes unavailable, so in this instance, the top one is unavailable, MQ will, of course, automatically now send all the workload down to the one that is still available. So you've got availability benefits as well as workload balancing benefits because of the cluster workload balancing. Of course, when you consider things like fault tolerance and availability, we do need to consider where can messages get stuck when there is a failure, because it's not quite as simple as what I had in the previous slide, because there are a number of points where you need to think about what might actually happen if there is a failure. So messages can get stuck in several places on one of the many queues that are used between the client and the service. So we have a transmission queue on the sending queue manager, we have a target queue on each of the service queue managers, and we also have a transmission queue that's used on the way back on the service queue managers as well for the replies. And at any of those points, a message could become stuck, as it were, if there was a failure for that queue manager while the message was on that queue. So let's have a look at what happens in various different scenarios if we have different types of failures. So the first thing we'll look at is what happens if the service queue manager or the machine that it's running on fails. So we lose that top queue manager, and also obviously the service that it's communicating with is now not able to operate either. Now we have, first of all, we have some messages on the transmission queue, the cluster transmission queue on the sending queue manager. And some of those messages might already be destined to go to the top queue manager. They're just waiting to be picked up by the channels that would have sent the messages over to that queue manager that's now failed. When MQ sees that the channel is stopped to that queue manager, then it's able to reallocate those messages. It goes through a process known as reallocation, which essentially means that for all messages that are not bound to that specific queue manager, and I'll come back to what that means in a second, all those messages that can be reallocated, they will now be diverted to another queue manager in the cluster where that queue exists that's available. So in this case, those messages can now be sent to the other queue manager. So they still get processed rather than remaining stuck in the transmission queue until the queue manager comes back up. Now, what did I mean by messages that are bound to a specific queue manager? Well, you might have noticed that in the MQ Open API call, there are many options that you can use, and some of those are bind options. So you can say whether you want the queue manager to be bound on open or not bound, essentially. Binding means that when the MQ Open happens, is the queue manager where those messages are going to go to decided at that point? And for the lifetime of that handle, are they all going to go to the same point, the same queue manager, sorry? Or does it mean that we can be a bit more dynamic and we can reallocate messages dynamically or workload balance them to different queue managers based on which one is most appropriate at the time. So if your applications want to take advantage of this ability for messages to be reallocated to different queue managers in the cluster, then they shouldn't bind the messages to a specific queue manager in the cluster. So the other place where messages can be stuck when the queue manager goes down is, of course, on the queue manager itself that has failed. And in this example, we have two queues that might have messages on them. We have the actual service queue, and we also have the transmission queue for the replies. Unless you're using ZOS and queue sharing groups, we can have shared queues which are usable by more than one queue manager at the same time, so that messages could be visible by another queue manager. The only way for you to get access to those messages, unless you're using shared queues, is to restart that queue manager. So that's what you need to do as quickly as you can in order to get access to those messages again. Now, there are, of course, various technologies in MQ these days for building highly available queue managers and for getting them restarted as quickly as possible. You could use any of those. And once you do restart that queue manager, then the replies will be able to flow back from the transmission queue. And as long as you restart your service, which you can do in various different ways depending on where your service is running, then those messages on the request queue will be able to be processed and replies sent back. So that's how we deal with that sort of failure scenario with a cluster. There are other scenarios, of course, including what happens if it's only the service that goes down. So normal situation is that messages flow to both queue managers where we have the same cluster queue defined. They get processed by the service that's connected to that queue manager. But if we lose one service, then does MQ know anything about that? Well, the answer is no, it doesn't, because the routing happens in the cluster, or the workload balancing happens on that queue manager on the left, which is sending the messages. And it doesn't know whether the messages are being processed or not from the request queue on the queue manager on the right-hand side. So what will happen in this case, it will continue workload balancing the messages that are sent to both queue managers equally, and the ones that get sent to the bottom queue manager will get processed as usual, and the ones that get sent to the top queue manager will actually start building up on the queue because there is nothing processing those. And eventually you might get a big buildup of messages, and that might cause all sorts of other problems in your queue manager as well, other knock-on problems like queue being full, or maybe you might even take up a lot of storage and cause knock-on effect as well. So we want to try to avoid that situation happening, and the way of doing that is that you need to add some extra monitoring. So you need something outside of MQ to monitor for that situation and try to do something about it when it happens. Now you can put in your own method of monitoring and resolving the situation, but MQ does provide a sample monitoring service, which you can run on each of the queue managers where you have these cluster queues. MQSCLM is the name of the sample that we send out with MQ. And what that does is to monitor whether there is something consuming messages off those clustered queues. So it looks for the open handles on those clustered queues as a sign of whether something has those queues open and is consuming messages off them. So it regularly checks for whether that's happening, and if it sees that some sort of outage has happened to the service, it will then alter the attribute on the clustered queue that will mean that it will now not be considered by the workload balancing algorithm for sending more messages to it. So what I mean by that is there are various attributes that we can set on our clustered queues that make that queue more or less important for the workload balancing algorithm when it decides where to send messages. Now, when that monitoring application sees that the service isn't consuming messages off that queue anymore because it doesn't have an open handle anymore, it will change the attribute on the queue. It's called the cluster workload priority, to make that priority lower than the other, than the queue and the other queue manager. And that will get, that information will get reflected back up to the full repository, and it will get used by the workload balancing algorithm on the queue manager on the left, which will now only send messages to the other queue manager and stopping the buildup of any more messages on that queue manager with a failed service. Now, we still might have a couple of messages on that queue manager that were already sent up there before the service failed. There is also a mode that you can run the monitoring service in where it will redrive those messages through the cluster, essentially, so that they can end up being moved down to the lower queue manager. So I'm sorry, I'm not quite getting my speech in sync with the animations here. Right, so that's what I was saying about redriving the messages through the cluster and getting them sent down to the service that's still running. Now, this method of monitoring and resolving the problem is obviously only suited to steady state applications. So these are ones where things are generally the same. So that service is connected to the queue manager and has an open handle on that queue to get messages for quite a long time. We don't expect the service to come and go rapidly. So if that was the case, then you might want to look at some different attributes and decide whether it's still alive or not. And there's other things that you could do as well if you wanted to make this service more intelligent. So you could look at whether the current depth of the queue is building up, for example, and compare it maybe to the depth of the queue and the other queue manager. So what we provide is just a sample. Feel free to extend it as you wish. So far we've looked at failures that happen on the right-hand side, where we have the service and the service queue managers running. Let's have a look at what happens if there's a failure on the left-hand side queue manager, on the client side, because that's also perfectly possible as well. So in this case, the reason that this is a problem in this diagram is because we have a single point of failure. We only have one queue manager that is that has a client connected to and is being used to send messages to the service queue managers. The solution to that, of course, is to have more than one. So we no longer have a single point of failure. Now that client can connect to either of those two queue managers. And when it puts messages to the cluster, then using either of those two queue managers, they'll get routed as usual over to the service. And the requests can also be routed back to the originating queue manager. So that's probably quite important because your application might well be doing a sort of request reply style of messaging, where it sends a message into the cluster and expects to get a reply back in the form of a message back to the same queue manager that it's connected to, so it can get those messages off the queue. And the cluster will do that. So those were fairly simple ways of using the workload balancing characteristics of the cluster. You can do things that are a little bit smarter as well and more complicated. So let's have a look at a couple of examples of that. So let's consider this situation where you have two sites, say one in the USA and one in Europe, and you have a client and a service running on each of those. And you're using clusters, of course, and you've got a service site running in New York and one in London. Now, the clients could send messages to either London or New York, and they would be processed just as well in either of those sites, but you probably want to, in a normal situation at least, want to have requests stay within Europe and within the US, because otherwise they would be crossing the Atlantic, and that would add latency and decrease the performance of your applications. So normally you want to prefer your traffic to stay geographically local. But you might want to be able to fail over to another site if something happens to one of the sites where the service is run. So if we lose the London site, for example, it might make sense for the request, the client request from Europe to now be processed by the New York site, because although it might take a little bit longer, you're still actually getting those requests satisfied. So can we do this with the cluster? Yes, you can. And this is the way, one way that you can set it up. So now we have a queue that's used for requests, and we have a request queue, rec queue. That's where we expect the request from the client to come to, where the service will get the messages off. If you now define a alias queue for that queue that's in the cluster, and you give it a high workload priority, so we define that queue alias called NYQ on the New York queue manager with a high priority within the cluster. And we define another one on the London queue manager with a much lower workload priority. So this cluster workload priority is the same attribute that I was talking about when we were looking at the monitoring service a couple of slides ago. That's the one that gets altered by the monitoring service to make one queue preferred over the other. And we're using it again in this situation. Now, if you define another alias queue on the client queue manager that points to that NYQ alias queue, now that application can put messages to that app queue, regardless of where it's running, whether it's in London or New York, so your application can stay the same on both sites. And we essentially define the same thing, but in the inverse, where the priority is concerned for the London queue as well. Now, what's going to happen because of the priorities is that if a message gets put by a client in London, if all the queue managers are running, then that message will always go to the London queue manager, because that is the queue manager, that is the queue, the LON queue with the highest priority in the cluster exists on the London queue manager. So as long as that queue manager is running, that's where that message is going to end up. Now, if that London queue manager goes down, then the cluster will route the request to the other remaining queue. Even though it has the lower priority, it's now the only remaining queue where the message can go. So that's where the message is now going to go. So that's how we achieve the message going to the local queue manager if it's running, or to the remote queue manager if it's not running. And that's all done automatically by the cluster workload balancing algorithm. Now, there is another way that you can do this. I'm not going to go into great details about this. You can look in the notes in the PDF of the slides if you want, because we've actually got the commands to define the channels and the queues that we need to set this up, and a bit more explanation about how to do it. But you can use two clusters as an alternative to the previous scenario. And because queue managers can be in more than one cluster, you have your service queue managers in both clusters, so that the clusters overlap at that point, but your client queue managers are in only one cluster. And the way that you can set this up to achieve the same thing as the previous scenario is by using that cluster workload priority attribute, not on the queues this time, but on the channels that are used within the cluster. Right, so we've looked at how clusters can be used for workload balancing and availability. Let's have a look at some concerns about different types of traffic that you might have within your cluster and how you might want to separate things within your cluster. So you probably have lots of different types of data going over your MQ network. So you might have some real-time queries, for example. So those are maybe fairly small pieces of data that you want to get from one end to the other very rapidly. So latency is important in that case. You might have some big pieces of data flowing across as well, where you probably just want to use your channel as efficiently as possible, regardless of what the latency is. You might also have some events going across MQ channels where it's not important how long they take to get there, but what's important is that they do actually get to the other end at some point. So there's various different types of traffic that you often have going through your MQ network. And when you're doing this in a cluster, and if you're doing it between two different queue managers in the cluster, all those different types of data will all be going across a single channel between those two queue managers. because within one cluster, you have one automatically defined channel between queue manager A and queue manager B. That's how it works. Even if you define multiple cluster receiver channels, so you might get multiple channels between the two different queue managers, you still can't say that you want a specific type of traffic to go through this particular channel and a specific type of data to go through another channel. So the way that you can resolve that is to, or one way you can resolve that is to have multiple clusters, because remember, queue managers can be members of more than one cluster. So you can have a cluster for each different type of workload, with each queue manager part of all those clusters. And now you've managed to separate the different types of messages between different channels that are used in different clusters. So that just keeps things separate and keeps things from impacting on each other, and lets you probably tune your channels as well for best performance for those different types of workload. There's other ways as well that things can interfere with each other. Different types of work can interfere with each other within a cluster, just as it can outside of a cluster. Let's have a look at another example, which is how the workload balancing might not always achieve what the intended effect is. So remember that the cluster workload balancing happens on a channel basis. So the queue manager on the left will send roughly half of the messages up to the top queue manager and half of the messages down to the bottom queue manager, or along half the messages along the channel to the top queue manager and half the messages along the channel to the bottom queue manager. So if we have, in this example, 150 messages put to that queue manager, 100 by client 1 and 50 by client 2, then we've got an even split of 50-50 messages sent to the two service queue managers. But of course, that doesn't mean that you're going to get a 50-50 split between the messages that are received by each service. So we've managed a even workload distribution between the channels and between the two service queue managers, but not between the messages that are actually processed by the services themselves, which might not be what you were intending. So solutions to this, well, you could split, again, queue managers into queues into different clusters, so that the workload balancing would then take place in two different clusters. And so you'd be able to get even workload balancing between the different services. And yeah, that's the way to get around that problem. So another thing that can happen is, another thing that you need to take into consideration is transmission queues within the cluster. So ever since clusters were first implemented in MQ, there has been a single transmission queue for all the data that is sent via cluster channels from a particular queue manager. So it's called System Cluster Transmit Queue. And any message that's going to be picked up and sent by a cluster sender channel from that queue manager is put under the System Cluster Transmit Queue, ready for one of the cluster channels to pick it up and send it to the destination queue manager. Now, there's a few problems with that, because it means that all your message traffic is going onto one queue, and all your message traffic to all the different queue managers is going to one queue. So if there's a problem with one queue manager, then that can lead to messages building up on the System Cluster Transmit Queue until it possibly gets quite deep. It could even fill up. If it fills up, then it will obviously impact messages being put that are destined to other queue managers within the cluster. So you've got a problem with one queue manager now starting to interfere with other queue managers in the cluster. Even if it's very deep, it might possibly start impacting performance. Or if the queue is very heavily used, that might also impact performance as well, which would impact messages going to all queue managers in the cluster. It also makes it more difficult to manage the queue, because you don't have a good way of knowing which how many messages there are on that queue that are destined for each queue manager within the cluster, and managing how deep it is or how many messages it can possibly hold for different queue managers within the cluster. So it makes monitoring and management of that queue more difficult as well. So what happened a number of years ago now, MQ 7.5 and version 8 is actually quite a long time ago. But what we did was to add the ability for you to configure multiple cluster transmission queues for each of your cluster queue managers. So there's two options when you want to configure this. You can either have MQ do it automatically. And the way that you set this up is that on the sending queue manager, you set the def CLX queue attribute on the queue manager definition. You set that to channel. And that tells the queue manager that it should create a new transmission queue for each channel, each cluster channel that gets started by that queue manager. So in a cluster where you've got channels being sent to 3 different queue managers, then the queue manager will automatically create 3 different cluster transmit queues for each of those channels that go into remote queue managers. The other thing that you can do is to, if you want a bit more control over your cluster transmission queues, then you can create them manually. So what you can do in this situation is on the sending queue manager, again, you can create your own transmission queues. So it's a normal transmission queue, but with the extra bits that you specify this CLCH name attribute. And what that says is that any cluster channel that is started that matches the name specified in that attribute should use this transmission queue. And you can use wildcards there too. So multiple channels can use the same manually defined transmission queue. And if you use a good naming convention for your cluster channels and your clusters, then you can achieve things such as, for example, having a specific transmission queue for each cluster. So we have, in this example, a green.xmit queue, which is used by all cluster channels that start with the word green. So any queue manager that's in the green cluster will use that transmission queue. Sorry, channels to any other queue manager in the green cluster will use that transmission queue. And if you were to define a pink XMIT queue, then any channels to queue managers in the pink cluster would use that one. So you've managed to now separate out the messages for 2 different clusters onto 2 different transmission queues, so they don't interfere with each other. An important thing to note here is that the default behavior now is to go back to using whatever the def CLX queue attribute on the queue manager says. So if there is a manually defined cluster transmit queue that matches the name of the channel, then that one will be used. If there is no manually defined cluster transmit queue for a particular channel, then it will look at what the queue manager def CLX queue attribute says to do. So that's whether creating an automatic one or use the system default transmit queue, system default cluster transmit queue, sorry. And that's what will happen in that case. So I've actually almost finished now, a little bit earlier than I expected to. Went through that quite quickly. So we have looked at what a cluster is and how to define one and what are the benefits from doing that. So we looked at the benefits of easier administration, also availability, and also that workload balancing, which will give you various benefits in terms of routing and availability. And finally, a little bit of smarter things that you can do, and also how you can separate different traffics within your cluster, which might be important to prevent failures in one place from impacting of creating other impacts onto your MQ estate within your cluster. So I went through that quite quickly. I finished a little bit early, sorry about that. Are there any questions that anyone would like to ask at this point?
No, there don't seem to be any further questions. So thank you very much, Gwydion. Very interesting. And hope to see some of you folks next Tuesday for further MQ sessions. Don't forget to fill in your feedback form, please. And thank you all for attending. Thank you, Gwydion.
Thank you.